Hello guys, this is Dr. Maha Abdurrahman. I'll be facilitating a tutorial today for the AQA IGCSE Stoichiometry. Let's start with the first question. It's an acid-base reaction. I can see here that my base is carbonate, sodium carbonate. I'll have here my salt over there. I have water and carbon dioxide gas that is released. Okay, so explain why the effervescence is seen during the reaction. Obviously, it's due to the release of carbon dioxide gas, as you see here. Okay, now let's move to the calculations. Their dilute acid, of course, that's a titration reaction. Dilute acid was titrated with sodium carbonate solution. He placed 10 centimeter cube, that's the volume of my acid, 0.1 mole per decimeter cube, that's the concentration of the acid in the flask. And then he used, as you see, methyl orange as indicator. Obviously, guys, you need the indicator here because as you see, the acid is soluble, it's aqueous. The base as well is an aqueous base, the salt as well an aqueous. So obviously you need a sign to show you that we have reached the neutralization point, because you won't be able to identify the neutralization point until you add indicator like the methyl orange. All right. Okay, then you continue your titration with sodium carbonate solution. He gave you here the volume of the sodium carbonate solution, which is 16.2 centimeter cube. That was added to the acid until the neutralization point. The first question, they want you to indicate the color of the methyl orange that will be placed in the acid, the hydrochloric acid. Basically, methyl orange is red in acidic medium and it's orange yellow in basic medium. So the answer here would be red. Now let's move to the calculation part of it. How many moles of hydrochloric acid were used? Obviously, when you see here, I'm gonna use my triangle over there. N equals C times V. N are the number of moles, and then I have, I'm just trying to move this on the side. Then I have C is the concentration, V is the volume in decimeter cube. I think all of you is familiar with this triangle. All right, so simply to find the number of moles of the hydrochloric acid, I need to multiply the concentration, which is 0.1 times the volume here, guys, is centimeter cube, so don't forget to divide it by 1,000 to convert it to decimeter cube. So it's gonna be 10 over 1,000. The total answer will be, let me use my calculator, it should be 0.001 mole. All right, that's the number of moles of the hydrochloric acid. Okay, now let's move to the next question. Use your answer in BII and the equation for the reaction to calculate the number of moles of sodium carbonate that has been reacted. Obviously, the ratio here is 2 to 1. So that means the moles of the sodium carbonate over there should be half of the moles of the HCl. So all what I need to do is dividing the number of moles of HCl by half. All right. So let me do that. It's gonna be 0.001 divided by 2. That will give me 0.0005 mole. Don't forget to write the correct number of zeros in the figure. Now the third question, use your answer in B III to calculate the concentration of the sodium carbonate solution in mole per decimeter cube. Since here, guys, we have the number of moles of sodium carbonate, and they gave us here initially the concentration, so I can simply use the triangle again to find the, I'm sorry, here they give me the volume, so I can use my triangle here to find the concentration. Since I have the n, the number of the moles, and the volume, I'm just gonna divide them together. Don't forget to convert this to decimeter. Let's do that. Okay, so simply let's divide the number of moles, which is 0.0005, divided by the volume. Now the volume, just let me check again how much was it. After dividing by 1000, it's gonna be 0.0162, and then let's do the math. It will be, just give me a minute, 0.0162 equals, so the answer would be the answer should be 0.031, okay, after rounding the answer. So this is the concentration of the sodium carbonate given. Now let's move to C. In another experiment, 0.02 mole of sodium carbonate were reacted with excess hydrochloric acid. Calculate the maximum volume of carbon dioxide gas that would be made in this reaction. Okay, having said that the hydrochloric acid is the one in excess, that means the limiting reagent is really the sodium carbonate, which I'm going to use to find out the number of moles of carbon dioxide gas. And once I get the number of moles of carbon dioxide gas, I can simply calculate the volume. All right, using again this triangle. I hope we all remember it. And we mentioned during our classes that this triangle is only used for gases. The volume of the gas in decimeter cube should equal to the number of moles multiplied by 24. 24, for those who don't remember, is the volume occupied by 1 mole of gas at room temperature and pressure. And since we are working here at room temperature and pressure, as mentioned in the question, that means that this equation is valid. All right. So let's check now how to find out the number of moles of carbon dioxide if I have the number of moles of sodium carbonate. Let's go back to our equation to find out the ratio. The ratio, as you see here, is 1 to 1. That makes my job very easy. That means the number of moles should be the same if the ratio is 1 to 1. So the number of moles I have for carbon dioxide is the same. So I can simply find the volume just by multiplying this number of moles times 24. Just give me a second to do the calculation. It's gonna be 0.48 decimeter cube. Here the answer always for this volume will get you will give you the volume in in decimeter cube directly. Okay, that was question 1. It was easy. There's nothing hard about it. Let's move to question 2. Question 2, they're integrating the hydrocarbons along with the stoichiometry. Okay, so what's meant by hydrocarbon? What's meant by hydrocarbon? We mentioned before about hydrocarbon. I'm just gonna drag my text over here to write. So hydrocarbon simply is organic compounds that contain carbon and hydrogen only. And don't forget to write the word only. Okay, so they're organic compounds, write that, that contain hydrogen and carbon. Sorry, did I mention oxygen? I meant hydrogen and carbon only. All right. And I have to mention the word only. Why do I need to stick to the word only? Because actually most of the organic compounds, they do have hydrogen and carbon, right? But only the hydrocarbons are the ones that contains hydrogen and carbon only. So actually from the name hydrocarbon, so basically they should contain hydrogen and carbon. Just don't forget to add the word only to get your full mark. What's the general formula of straight alkane? I think we emphasized on that when we were explaining our lessons. Alkanes are CN H2N plus 2. This is the general formula of alkane. For alkene, it's CN H2N. So you get your 3 marks over there. Now let's go to the calculations. Okay. This one, it's a hydrocarbon. It's not only an hydrocarbon actually, because it does contain oxygen. So you have carbon, hydrogen, and oxygen, but it is an organic compound. It contains 54.54% carbon, 9.09% hydrogen, and 36.37% oxygen by mass. Find out the empirical formula. Just to remind you what the empirical formula is, it just gives you the ratio between the elements forming a specific compound. So the elements that are forming this organic compound is carbon, hydrogen, and oxygen. I simply need to find out the ratio between them, but this doesn't mean that this is the true molecular formula. It just represents the ratio between the elements forming this particular compound. How can I find that? Just 2 steps. The first step, I'm gonna divide every percentage mass here by the MR, or by the AR actually, which is the atomic mass of each element. So for the carbon, the atomic mass is 12. So I'm going to divide 54.54 divided by 12 to find out the number of moles of carbon in this molecular formula. It will give me 4.5. Okay, now let's check how many moles of hydrogen do I have here. I'm going to divide 9.09 divided by 1. It will give me the same thing, 9.09. I remember, guys, we said when you have this small number, you can just ignore it and round it to 9. Okay. Then finally, the moles for the oxygen is 36.37 actually, divided by 16, which is the molar mass or the atomic mass of the oxygen. It will give me 2.27. Okay. All right. So as you see here, if I'm gonna to find the ratio between them, I need to divide by the smallest number. So that was really step number 1. We just divide the percentage by mass over the atomic mass for each element. Then the step number 2, which is dividing each one by the smallest number to find the ratio between them. Okay, so the smallest number should be 2.27. So 4.5 divided by 2.27, it will be, which is the ratio for the oxygen, right? And then it should be, no, sorry, that's the ratio for the carbon. Okay, let me just do the calculation over there. 4.5 divided by 2.27, it will give me 1.9. 1.9 is almost 2, so I'm gonna round it to 2. Okay, then let's divide the hydrogen. Let's write the hydrogen. 9 divided by 2.27, it should be 9 divided by 2.27, which is 3.9. Again, this one I can round it to 4. Then finally, the oxygen, since I'm dividing it 2.27 divided by 2.27, the answer will be 1. So the ratio is simply 2 to 4 to 1. So don't forget to write the empirical formula after you find the ratio, the third step. Don't forget to write your empirical formula. That's a common mistake by many students. Actually, the mark you will get if you write this properly, so that's 1 mark. The second mark is for doing the first step. Okay, I hope that was understandable. Now let's move to, usually when you find out the empirical formula, they want you to find or to use the real molecular formula of compound X, providing that the MR is 88. All what you need to do is dividing the MR, which is 88, over the MR of the empirical formula. Now to find the MR of the empirical formula, which is C2H4O, we're just gonna use the periodic table for that. It's gonna be 44. I think all of you guys know how to calculate the MR for compounds. Just when you look at the periodic table, don't forget to pick up the bigger number, not the smaller, because the smaller is the atomic number, and I'm looking for the atomic mass, so don't forget to add up all the atomic masses. I use the correct one. You will find that the MR for this empirical formula is 44. Divide the 88 by the 44. This will tell you that how many times the molecular mass is bigger than the empirical formula. When I do the division, I'll find that the molar mass or the molecular mass of 88 is bigger than the empirical formula by 2. That means the molecular formula should be twice as big as the empirical formula, right? So I'm just gonna multiply that by 2. So it's gonna be C4H8O2. This is the molecular formula of my compound X. And don't forget to write down the molecular formula. So that's 1 mark. You get 1 mark over here. You get 1 mark over there. Okay. Now let's move to part C. Okay. So that's another part. It's an ester. If you remember the ester, we explained that in the last class of organic. Ester has a molecular formula of this. And then they want you to name and give the structural formula of 2 esters, 2 different esters with this molecular formula. Okay. First of all, I would start with the structural formula to make my job of naming the ester easier. So I would start with the structural formula. What's the functional group of the ester? Let's start with it, because that should be fixed in both esters. C double bond O, O, right? I would write my C double bond O, O here, and as well my C double bond O, O over there. That's the common thing. And then let's look at the molecular formula. How many atoms of carbon do I have? 3, right? So I can simply place one over there. Okay, since here I have C, I should have a CH3 over there. And the other one, which is I already have C here, if you notice. So I end up by having only one missed carbon. I'm going to add it over there as another CH3. Okay. Now, the only one, the structural formula, but just for you to understand how the bonds are formed, I'm going to draw the displayed formula as well. So that's the carbon with the 3 hydrogens over there. The carbon should be connected to the other carbon over there, right? This other carbon is having the C double bond OO, which is over there. That's the other O for the ester. This is the ester functional group. And then from this oxygen, it will bond to that carbon over there. And then this carbon need to have 3 hydrogens. Now, if you check here, how do I know my formula is correct? Each carbon is surrounded by 4 bonds. Check this one. This carbon, 1, 2, 3, 4. 4 bonds, so that's correct. The oxygen need to have 2. This oxygen as well has 2 bonds, so that's correct. How about this carbon? This carbon has 1, 2, 3, 4 bonds around it, so it's correct. This carbon as well has 4 bonds, so my displayed formula is correct. My structural formula is correct. And most important thing, does these numbers matching the molecular formula? I have to count. 1, 2, so there's 2 oxygen, 6 hydrogen, 3 and 3 is 6, and how many carbon? 3, 1, 2, 3. So also it matches my molecular formula. The only thing that left here for me is to name the ester. We agreed that the carboxylic acid is the parent, is the father part, that I always relate the ester to it. So I would call it methyl ethanoate. Methyl ethanoate. So it's coming from ethanoic acid. I would name it methyl ethanoate. How about this guy over there? I just drew C double bond OO. I still need to arrange 2 other carbons with their hydrogen. I would put 2 carbons over here because I already had placed 1 carbon over there. So let me try to put 2 carbons over here. C2, it should be H5. Okay, this will leave me by 1 hydrogen here. How would I know? If that's hard for you to guess, just simply draw your displayed formula. Let's assume that I don't know what the structural formula is. Let's try the displayed formula. C double bond O, which is this one. O, that's the ester bond. And then I have C2H5, that's a carbon, another carbon. Let's just distribute the hydrogen. I'll have 1 here, 1 here, 1, 2, 3, 1, 2, 3, 4, 5. That's right. So it's C2H5. Now this oxygen has 2 bonds, so I'm good. This carbon has 4 bonds. I'm good. Now that carbon over there has 1, 2, 3, 4. No, actually it has 1, 2, 3. So I need to add another hydrogen over there. Okay, so this is correct. Let's count. I have 1, 2, 3. That's correct. 6 hydrogen. 1, 2, 3, 4, 5, 6, and 2 oxygen. So this formula as well is correct. What would I name it? Where is my acid? Is over here. It's the methanoic acid. And my alcohol is the C2H5, which is the ethanol, right? So I would call it ethyl methanoate. This question is a challenging question. It's attainable, you can still solve it, but it needs some patience, it needs like actually multiple information. It needs that you know exactly what's the functional group of the ester, you know how to draw a proper displayed formula, and you need to know how to name the ester. So it's a kind of combined question, has 4 marks. Okay, name the ester produced. I'm doing D now. Do the ester produced from the reaction between propanoic acid and methanol. This is the father, this is the one I'm relating to in the name of the ester, so I would call it propanoate. I would refer to it as propanoate because of the propanoic acid. Methanol will make this radical, which is the methyl group, so it will be methyl propanoate. Methyl propanoate. Now let's move to, okay, for E, it's out of scope of the AQA IGCSE. This is a condensation polymerization and it's out of scope of the AQA IGCSE, so I'm gonna skip it. Moving to question 3. Question 3 should be a piece of cake because it's typically like the other question that we have solved before. They're giving you the percentage of carbon, hydrogen, and oxygen. And they want you to use the percentage to calculate the empirical formula, just like what we did in the previous question. And then they're giving you the MR to find out the molecular formula. So it's typically the first question that we solved. How does this prove that compound X contains only carbon, hydrogen, oxygen? Simply if those 3 percentages making up to 100, then this compound only contains carbon, hydrogen, and oxygen. But what if I add up those percentage and I found out that it does not add up to 100? That means that there is another element that is forming this compound. Let's add them together. If I add them, I will find that they all add up this percentage. All percentages add up to 100%. So that proves that it only contains carbon, hydrogen, and oxygen. Use the above percentage to calculate the empirical formula of the compound. Same thing, exactly the same steps. So let's start with the carbon. The carbon, I'm gonna divide 55.85 divided by 12. This will give me, let me do the calculation, give me a second. 55.85 divided by 12. It's 4.65. Let's do the calculation for the hydrogen. 6.97 divided by 1 should be the same, 6.97. And then the last thing, which should be the oxygen, 37.18 divided by 16. Take care, guys, don't do O2. Don't do 16 times 2 by 32, because here you're only dividing by the atomic mass of one oxygen, which is 16. The answer should be 37.18 divided by 16. It should be 2.32. Now the next step, I need to divide by the smaller ratio, right? So let's divide by the smaller ratio, or by the smaller number to find the ratio. I would divide for the carbon 4.65 divided by 2.32, that will give me nearly 2. Yeah, nearly 2. And then I have my hydrogen over there. The ratio of the hydrogen 697 divided by 2.32, which should nearly give me 3. Then I have my oxygen over there. My oxygen is 2.32 divided by 2.32. It will give me 1. So I will end up by having empirical formula of C2H3O. This is the empirical formula. Don't forget to write it. Back to the molecular formula. I'm just going to divide 86 by the MR of this empirical formula. So 1 mark, I'm going to just put this over there. So I need to have, actually, let me just double check. Yeah, this is a 2-mark question. So the second mark should be for finding an MR of the C2H3O, which is going to be 43. So just dividing 86 over 43, it will be 2. That means this molecular formula is bigger than the empirical formula by 2. So I can confidently write my molecular formula, which is, don't forget to write it, C4, because I'm going to multiply that one by 2, H6O2. This is my true molecular formula, and I got the 2 mark for this question. Now, if you remember, guys, this is the test for unsaturation, the bromine water, if you remember all of it. Bromine water changes from brown to colorless when we add the substance X to it. What does this tell you about structure of X? It tells me that for sure it contains double bond, right? It contains double bond. I remember we emphasized that the bromine water, decolorization of bromine water, is proving for having the double bond. Now, magnesium powder reacts with an aqueous solution of X. Hydrogen gas is evolved. Usually the reaction of metal plus what will give me hydrogen released as gas? Usually metal plus acid, if you remember, it will give me hydrogen gas released and salt. By using this information, I would deduce this X has, or this X is an acid, right? Because it releases hydrogen ions as hydrogen gas. Our releases H plus ion. So that means this is this substance X is an acid, right? Since guys this is an organic acid, لأنه it has carbon, hydrogen, and oxygen. Organic acid is the, what do we call them? Carboxylic acid. Organic acid are called carboxylic acid. Now let's come to the challenging part. A little bit challenging to draw the structural formula of X. As I always advise you, draw the displayed formula first. Don't try to, then the structural formula. Don't try to draw the structural formula directly. Okay, that's my molecular formula, C4H6O2. Don't forget, that will be your guide. And I have a double bond and I have a carboxylic acid. So those are my 3 guides that I'm gonna use. First of all, this compound for sure contains 4 carbon, as you see here. So 1, 2, 3, 4. Let's start by drawing these. Then for sure it has a carboxylic acid functional group, which is C double bond OOH. This for sure I have these. And if you look here, it has 2 oxygen. So this really matches with the formula I'm deducing. And then I just need to fill the hydrogen out. But keep in mind that this structure X also has a double bond. That's why it decolorizes the bromine water. Where should I put my double bond? I would put it, you can either put it here, okay? Or if you choose to, let's think, I erased all of it. Let's say another student doesn't want to put the double bond here, she can still put it over there, okay? Type. I have a question. Can I put the double bond over here? Let me just remove this. Oh. Okay. My question is, can I add my double bond over there? No. Why no? Because look how many bonds around this carbon I will end up by having. 1, 2, 3, 4, 5. So I cannot put the double bond at this position. Okay, so just gonna go back to, let's say I wanna do the double bond over here. Now let's put back, arrange the hydrogen I have. I already have 1 here, so I end up by having 5 hydrogen. Okay, here, this is already full, 1, 2, 3, 4, so I'm not gonna add any hydrogen here. Please guys, don't add a hydrogen over there because this is wrong. Okay. Here I have 1, 2, 3, so I'll add the hydrogen over there. And then this one has only 1. This carbon has only 1 bond, so I need to add 3 more over here. 1, 2, 3. But there's a missing hydrogen. 1, 2, 3, 4, 5. And it tells me the hydrogen should be 6. Where's the mistake? It's over there. 1, 2, 3. Those are only 3. So I need an extra hydrogen here to have 4 bonds around this carbon. So for sure, this displayed formula is correct. This is a displayed formula. But do they need displayed formula? No, they want structural formula. But it would be very easy to deduce the structural formula from the displayed formula I drew here. I'm just gonna copy it again. CH3, CH, CH, COOH. Okay. I'm hearing someone saying, can I, how should I show the double bond over there? You can write it like this, CH3, then CH, double bond, CH, COOH. You can do that, or you can do that. Both are correct. All right. Now let's move to the question 4. Okay. Question 4 is an acid-base titration as well. 2 salts can be made from potassium hydroxide with sulfuric acid. They are potassium sulfate and the acid salt potassium hydrogen sulfate. Those both can be made by this titration. Okay, so 2 salts can be made by titration of sulfuric acid and the potassium hydroxide. Let's have a look. Okay. He gave me the volume, that's not the concentration, that the volume of potassium hydroxide solution, which is the base. So let me highlight it. Sorry, just a second. go. Okay. Okay, bear with me until I find my document again. Here we go. Here we go. Okay. So this is the volume of the potassium hydroxide, and that's the concentration. Okay. It was neutralized by, that's the volume of my sulfuric acid in the burette over there. So those are the given information. Okay, that's the equation I'm gonna use. They want you to calculate the concentration of the sulfuric acid. The concentration of the sulfuric acid. Okay. To find out the concentration of the sulfuric acid, I need to find the number of moles of the KOH used first. Then from the number of moles of KOH used, through using, or by using this equation, all right, guys, I can find the number of moles of sulfuric acid. Am I right? And once I get the number of moles of this sulfuric acid, I can get easily the concentration of the sulfuric acid because I already have the volume over there. This is how all the neutralization or the titration reaction works. The good thing that they're helping you and they're giving you the steps, step by step. Okay, now let's find then the number of moles of KOH. I have here the concentration, I have the volume, just need to convert this to decimeter cube, and then I can easily find the number of moles from, I'm gonna write it again, volume, no, actually, sorry, it's the number of moles. Number of moles is the concentration times the volume. Now, let's do that. Okay. So the concentration is 2.53 times the volume is 0.025 because I already divided by 1000. The answer should be 0.0632. Those are the number of moles of KOH. I'm just gonna divide them by 2, right, to find the number of moles of sulfuric acid, because basically the ratio here is 2:1 as you see. So the number of moles of sulfuric acid needed to neutralize the KOH, I'm just gonna simply divide this by 2. Okay. So if I'm gonna divide that by 2, it will be 0.316. Okay, and then now I need to find the concentration of the sulfuric acid, and I have the number of moles, I have the volume. The volume is 28.2, so I'm just gonna convert it to decimeter cube. So okay, so the answer is, the final answer after I divided both of them will be 1.1 mole. Okay, I hope you all, that's after rounding, of course. I hope you all got this answer correct. Let's move to The next question. The next question, in the conical flask, there is a neutral solution of potassium sulfate, which still contains the indicator used in this titration. All right. Describe how could you obtain a solution of potassium sulfate without indicator. So they want you, of course, guys, in this experiment, we used an indicator to know how to indicate the neutralization point. But this question, we really need to think, what if I want to use how to obtain the solution of the potassium sulfate, which is the salt, but without using this indicator? What should I do? I can simply mix sulfuric acid and KOH, which is the base, in the amount of the ratio of 1 to 2. They need to have the same concentration. It's just the number of moles has to be doubled. How would I know that? From the equation itself. If you look here, the number of moles of KOH is 2 to 1, right? That's the ratio. So the number of moles has to be doubled. So to double the number of moles, I can just get double the amount of KOH, but the concentration has to be the same. All right? You can specify that in moles or in quantity. So you can say I can get 2 moles of KOH and react it with 1 mole of sulfuric acid. That's also a correct answer. Potassium hydrogen sulfate. Potassium hydrogen sulfate, which is this. This is the potassium hydrogen sulfate. It can be made by the following reaction. If you look here to compare between this reaction and the previous one to make the potassium sulfate, the ratio of potassium hydroxide to sulfuric acid was 2 to 1, while the other one, look at the potassium hydrogen sulfate, the ratio here was 1 to 1. So this is really the difference. Suggest how could you make a solution of potassium hydrogen sulfate, again without using indicator. So I can mix the sulfuric acid and KOH in equal amounts with the ratio 1 to 1 with the same concentration to have the same number of moles. Or you can simply add, let's say, equal number of moles for both KOH and sulfuric acid. This is also considered a correct answer. Okay, then they want you to describe a test to distinguish between the potassium sulfate and sulfuric acid. So basically that's a test to distinguish between, don't panic, don't say I don't know that, just this is an acid, right? And that's a salt. You just need to differentiate between acid and the salt. The simplest test that you can choose, there are actually multiple of tests that you can use, but the simplest one was by adding, or you know what, was by just measure the pH, right? I will find the pH of the acid is, or the strong acid would be between 0 to 3. This indicates this is a strong acid, which is the sulfuric acid, right? I can also add a litmus paper. If I choose litmus paper, the litmus paper with acid, it will turn to red. With the salt, there would be no change because, guys, the salt is neutral, right? It's not acidic, it's not basic. So here for the pH of the salt, I would expect it should be like around 7, I would say. This one is the easiest, using litmus paper. Acid will give me red, the salt will have no change. There are some other reactions that you can use to differentiate between them. For example, any test for acid, you can use any test for acid. Acid plus metal, if you remember, we said it gives me salt plus hydrogen. Okay, so this will only work with the sulfuric acid, while with the potassium sulfate, if you add metal, just add metal to the potassium sulfate, it will have no reaction. So those are multiple answers that you can choose any of them. Next, the question 5 is out of scope of Oxford AQA IGCSE, so I'm just gonna skip it. Last question, which is question 6. Predict the formula of each of the following compound. That's very easy, I hope. Aluminium fluoride, it's not very clear, but this is aluminium fluoride. So I'm just gonna write aluminium over here, and then the fluoride. Aluminium is in group 3, the oxidation number is 3. Fluoride is in group 7, 1 or -1 plus 3. Just do the cross multiplication thing, so it should be AlF3. And you know what? I would remove this in the exam. That's more than, because this one is more than enough. Okay, now let's check the arsenic oxide. Oh, I don't know where the arsenic is, right? So let's go back to the periodic table. You will find the arsenic in where is it? I'm still looking. Just give me a minute. It's hiding somewhere. You know what? I can't find it. It should be somewhere, but can't find. Oh, I found it. It's in group 3. It's actually in group 5. Arsenic is in group 5, just like the nitrogen, arsenic oxide. But you know what? This question is kind of a hard question, because you won't be able to use, because that's not an ionic compound. Arsenic oxide is a covalent compound, just like the nitrogen dioxide. So it would be hard to predict, but the arsenic oxide is As2O3. Okay, it won't come in the exam because it's hard for you to identify, because that's, as I told you, this is not a ionic compound. Okay, طيب, let's move to the silicon bromide. The silicon bromide, I have SiBr, and this is group 4, this is group -1, so it has to be SiBr4. I'm just gonna remove these and write it properly, so it will be SiBr4. Okay, and now let's deduce the formula for each of the following ion. Phosphide, so just go to where the phosphate is. You will find the phosphate is in group 5. That means it has 5 electrons in the outer shell. They need 3 more electrons to have a complete outer shell. So it's P, and then I have a -3 over there. Okay. Barium, Ba. Barium is in group. It's not beryllium, It's barium, Ba, because you have beryllium. Beryllium is Ba. Barium beryllium is Be. This is the beryllium, and that's the barium Ba. Both of them is in group 2. That means it needs to lose 2 electrons to have a complete outer shell, so that will be the formula of the ion. Francium, where we have seen that francium is in group 1, Fr. That means it have 1 electron in the outer shell. It needs to lose 1 electron to have a complete outer shell, so the ion should be Fr plus 1. Last question, our last part of the question C. Draw a diagram showing the arrangement of the valency electrons in one molecule of the covalent compound carbon dioxide, and use X to represent the electrons from the carbon. We use O to represent the electrons from the oxygen. So you should abide, guys, to those symbols that he told you. X for the carbon and the circle for the oxygen. Let's draw that. I think we made a similar one in the class. Carbon dioxide, I have the carbon, right? And this is a covalent compound. Carbon should has how many electrons around it in the outer shell? 4, because it's in group 4. I'm going to refer to them as X's, as he said. Then I have carbon dioxide. There are 2 oxygens, one over here, one over there. Oxygen is in group 6, so it has 6 electrons in the outer shell. I would add 2 here, 2 here. The other 2 should be bonding with the carbon to form the double bond. And then here I have the other 2 over there. 1, 2, 3, 4, 5, 6. Now, why did I choose this arrangement? Let me just, to make it more accurate, I'm just gonna move these 2 and draw them again, just to have the angle properly adjusted. Now, that's correct now. Okay, now I was discussing why I had this arrangement. The carbon has to have 4 bonds around it. This is the 1 bond, 2 bond, 3 bond, 4 bond. Then when the carbon is bonding with the oxygen, now it has 8 electrons in the outer shell. So it's stable. 1, 2, 3, 4, 5, 6, 7, 8. So this is fine now. Let's check the oxygen. The oxygen has to have also 8 electrons in the outer shell, and initially it has 6 electrons because it's in group 6. 1, 2, 3, 4, 5, 6, 7, 8. Now the oxygen is good and happy. It has 8 electrons in the outer shell. The other oxygen as well has now, after bonding, 8 electrons in the outer shell. And this is the diagram that shows the valency electrons of the molecule of the covalent compound carbon dioxide. I use the symbols that they want to represent the electrons in the outer shell. I guess we will get the 3 marks if we drew this properly, showing the bonds. Don't forget the Venn diagram. This shows there are 1, 2, 3, 4 bonds, or 4, electrons in the double bond. Yani here you have 1 electron, 1 electron, 1 electron, 1 electron. لأنه each bond is composed of 2 electrons. This is a double bond, so I'm expecting to see 4 electrons shared over here, 4 electrons shared over here as well. 1, 2, 3, 4. This is the other bond that I am seeing over here. In the Venn diagram, those common areas are the double bond. Okay? Of course, don't do that. This is just for you, or for me to explain to you. Okay? I hope this tutorial was beneficial to you. I hope that you got most of your answers correct on the calculations. This worksheet was very beneficial because it was not only covering calculations, it was also covering organic chemistry, as you see. It was covering bonding, like covalent bond, as you see in this question. As well, also, it was covering the ions, as you see over there, how to write the ions. So it's covering more than one chapter. A lot of organic questions also came. I hope you find the tutorial beneficial for you. Good luck, guys, from the bottom of my heart. Thank you. See you next time. Bye.